Hi, my name is Yolanda Davis, and for my final project, I focused on credit card fraud detection using deep generative models.
The impact of credit card fraud is pretty vast. Worldwide, it's responsible for $28.65 billion of financial loss. Within the United States, there were 270,000 reported incidences to the FTC associated with fraud in 2019. So it has a pretty large impact. However, in the US, consumers are, for the most part, protected from fraud due to the Fair Credit Billing Act. They are only liable for a maximum, they're only liable for $50 no matter what the transaction was. However, that cost ends up being absorbed by merchants or financial institutions. And it's not just the incidence of that fraudulent transaction, they also have to pay for the investigation, any litigation, as well as any people or resources that were used in order to track fraud. There are a variety of different detection methods that companies use in order to detect fraud because, of course, they are vastly impacted and they want to mitigate it as best as possible. And anomaly detection is one of those common techniques used to identify whether or not transactions are abnormal or considered fraud. What anomaly detection does is it focuses on creating a model that learns the characteristics of normal behavior. So the key being, when normal behavior and normal characteristics are understood, any deviations or outliers from that normal behavior can be measured as some form of loss. And that measurement can then be used to classify whether or not something is normal or is a fraud or anomaly. Typically, these methods include clustering algorithms or regression models, but we also have seen more deep learning models come to the forefront. Some challenges in dealing with this type of data starts off with the fact that the data is usually imbalanced, where fraud, for example, in the case of credit card transactions, only represents 6.8 cents for every $100 spent. So it's definitely imbalanced where we only have a very small amount of fraud to determine characteristics in which it could be classified against. And so this leads to pretty poor recall rates where we could have greater instances of false positives because models which only see mostly normal behavior has a hard time trying to discern between what should be normal versus what's abnormal. Also, models may not support multivariate, so any multiple features within the model or having high dimensional features. And these aren't necessarily the deep learning based models, but more of some of the traditional ones like k-means or ARIMA, things that are time dependent, for example, tend to be univariate sometimes. Also, because if they don't support that multivariate capability, it might not be able to capture some of the feature interactions even at these higher dimensions. Especially within deep neural networks, we know that the layers allow us to capture certain behaviors and certain relationships that we are usually unable to see with more traditional or other types of learning. And so depending on the model that you choose, they might not be able to capture some of the interactions that would fully describe what a fraud anomaly looks like. Also, it might not handle noise well. So for example, if we see data that is mislabeled, which can happen from time to time, if models are only geared towards the data that it was trained upon, then, or if it's only geared towards normal data, I should say, then any error in that data could skew results. And it might not react well to that. When it comes to deep generative models, the goal here is using a model that can learn the pattern based on the input data. And that input data wants to generate a newer example that could have been chosen from the original data set. So basically, these models do a great job of learning its input such that it can be reproduced. And in the case of anomaly detection, we would want to turn this learning towards understanding and learning normal behavior and being able to reproduce that normal behavior. Deep generative models, they support multivariate and high dimensional data. We've seen this in various examples in class. And it also provides a method to account for imbalanced data. And we'll talk about that in some of the implementations from the study. The models that I researched were the Variational Autoencoder for this use case, as well as the GAN or Generative Adversarial Network. When it comes to anomaly detection with autoencoders, they're used in a semi-supervised way. So this is where we would have our normal data, like I mentioned before, that is identified from the training set separately from anything that is classified as an anomaly. And the normal data is used to train the autoencoder such that it learns what characteristics or how the normal data should be represented. Then once we're ready to test, that model is tested with a combination of both normal and abnormal data, with the goal being is we're going to flag, the model would flag any sample that has a loss that's large, that is much larger than what we were seeing in the normal data. So basically, if the model is unable to appropriately generate the input, there might be a flag that the input itself did not follow the normal characteristics of other data that we know is normal. Now, the challenge with the vanilla autoencoder is that it's not as generalizable when we give it input that it might not have seen before. So the variational autoencoder was created to account for this issue. And it does that because the latent space used to learn is a probability distribution for the input as opposed to being the actual input's representation in that latent space. So now when we actually get newer data, the autoencoder or the VAE actually will be able to demonstrate or to reconstruct something that's within the probability distribution of what's considered normal, as opposed to getting some novel input, not being able to see all of its characteristics well, and immediately classifying it as abnormal. For the GAN, it is trained similar to the VAE, where only normal data is introduced, and this is a particular implementation of ANOGAN that specifies this. The discriminator and the generator, they work against each other, just like in the GAN that we studied in class, where the goal is for the discriminator to try to properly classify between normal and anomaly, whereas the generator will generate noise input attempting to trick the discriminator. And then loss involves two different measures, just as before, accommodating the discriminator's loss as well as the generator's loss. And both of those loss might need to be accommodated or somehow correlated in order to create a score that's useful for anomaly detection. In order to do this experiment, I used the Kaggle credit card fraud data set. This had 287,000 records, and the data actually came obfuscated such that it only contained principal components from a previous pre-processing step provided by the person who posted it on Kaggle. However, there are some other fields such as time, amount spent, and of course the classification field, which were available. So all of this data was available to use, and it only contains 0.17% fraudulent transactions. So it definitely was an imbalanced data set. For the VAE experiment, I adapted a lot of what was in homework 12 in terms of how the encoder and the decoder was built, with the only caveat or changes made was the actual dimensions as we downsampled or upsampled as it was relevant. A lot of the training step is also similar to that homework in this use case, but I also added a test step in order to support cross-validation. Within this particular experiment, I did two different evaluations. One was a manual error threshold where I looked at the classification results. I saw the distribution of the errors and picked a line that I thought was the best threshold error given the distribution between known fraudulent error versus normal data error. And from there, I was able to get what I think is a reasonable recall score. However, as you can see, when it comes to the confusion matrix, there were a lot of observations that were still classified as fraud, but really were normal. Yet it did a great job in still identifying what was normal. However, when it comes to credit card transactions, companies may want to not alert consumers needlessly. I also did an automated version of this calculation of the threshold where I evaluated all the different precisions within a certain range of potential thresholds from 1 to 0.5. And so finding the best precision, or actually what would result in the best precision, was the goal in this particular case. So in this particular confusion matrix, we see that it does a better job in identifying normal records. However, it is definitely lacking in discerning fraudulent transactions where there were more cases that were deemed as normal than abnormal. In the GAN experiment, it was another situation where I derived that homework 12 into something that could fit for the credit card use case. It used 10 layers similarly to the previous homework. And again, the dimensions were adjusted to apply to this type of data. This experiment actually took a lot longer to train. So it was trained for 2,000 epochs, which took about 2.5 hours. The result of this experiment wasn't as great as VAE. When we look at the precision here, it was a bit more balanced. However, we still see that when it comes to fraud detection versus lack of fraud protection, when it comes to fraud detection, I should say, there were more records, again, that weren't classified well. It did do a bit better with VAE with the manual threshold, where it didn't classify as many normal as fraud. However, we're still concerned that what was classified as normal is still coming up as fraud, and there's a significant number showing here. So in summary, the main outcome for my particular study was that VAE outperformed GAN with a reasonable amount of skill as it relates to the precision scores and the recall scores that we saw. Also, VAE was superior in terms of training time. For my particular setup, it was minutes versus hours, and both were trained on Colab. GAN was definitely a challenge, and it was due to its instability. There's lots of articles that talk about how to best attempt to tune GAN if you see that it does not converge. So as demonstrated by the graphic that I have here, the GAN in my case of 2,000 epochs didn't converge in my final experiment. However, prior experiments, I've seen it converge and then not converge, which made it extremely unstable. And some of the conversations around this says that when the discriminator starts outperforming the generator, we see vanishing gradients. And I think that's what's going on here. What was good about working through this is that both models were easy to adapt to this case. So the homework itself was geared towards images. And even though I didn't have the ability to test the latent space and have something that I could render and inspect along the way, it was still good to see that there was some potential progress and some performant model in VAE that was classifying in a way that was performant or was reasonably skilled. And finally, both models, I believe, should be investigated further, especially in certain implementations, because there are lots of different implementations of these models. TDVAE is one that's focused on adding a time element to the learned representations, and it's geared towards sequential-based data. And when it comes to anomalies, I'm pretty sure we can detect certain cases where anomalies might show in certain times of the day or days of the week. And that might be something to try. as well as the least squares GAN or LS GAN. That can be another model that is used to counteract some of the things that I was seeing in terms of vanishing gradients. So I believe there is a lot of room for further studying this.